Here we have motion worksheet number 3, introducing equations for constant acceleration. In this worksheet, you will use your equation library sheet to help you choose the right big physics idea to solve this real-world problem that you're being asked about. The work you see here was done in class. Hopefully you have this down. This is a sheet from one class, so the work that you saw may be slightly different. With that being said, I'm going to jump ahead to the middle of problem 2. In this problem, we have a swimmer, Tracy, going forward in the pool and then back to where she started. Back to where she started. And that brings up that funny idea of displacement. What is the average velocity for the second half of the swim? Okay. Average velocity. We know what we're being asked for. Since there was a first swim and a second swim, I'm being creative and labeling this one V average 2. Previously I noted in class that the second displacement would be negative because it's backwards, in reverse. And what else do I need? I need the time. The second time is listed in the problem. I've already found my big physics idea. Velocity is displacement divided by time. V average 2 for her return swim is the displacement of the return swim divided by the time of the return swim. Okay, plug in my numbers. Okay, negative 50.0 meters. So details, details, details. Negative for direction. 50.0 because I keep my measurement. And always write your units. No naked numbers. The time is 22.0 seconds. Then I can pick up my calculator. Negative 50 divided by 22.0. Okay. 3 significant digits in the measurement divided by 3 significant digits. Our answer is going to have 3. 1, 2, 3. The 7 stays the same because its neighbor is a 2. Wait, there's a lot of glare. Its neighbor is a 2. Okay. Did she swim faster to begin the race or to end the race? Part C, average velocity for the round trip. Well, let's focus on the big physics idea. There's many ways that you could approach this. But again, I have velocity. I'm looking at the big physics idea picture here, right? And let's notice that it depends on displacement and time. Well, did she take some time? You bet. Let's focus on the idea of displacement. Displacement is defined as your final position minus your initial position. Said in other words, your displacement is how far away from your start you end up. And you take that fact literally. It is a different idea than distance. In fact, Tracy swam 100 meters, and that's what you would call the race for sure. This idea of displacement is incredibly useful when you want to talk about measuring work, when you want to be talking about measuring power. You use this concept because direction is so important. So if you're talking about displacement, Tracy went nowhere. And we are talking about displacement because velocity has a direction. Tracy went from 0 meters to 0 meters. Therefore, her displacement was 0. And I'll save you the boredom of showing her velocity would be 0. Okay, the only thing that I wish I had here was an equation sheet that matches yours. So instead I'll refer to it. Okay, step 1, read the problem and label. Sally travels by car from one city to another. She drives for 0.500 hours at 80.0 kilometers per hour and 0.750 hours at 80.0 kilometers per hour. What is her total distance traveled? Okay, I notice they're talking about distance, not displacement, so I don't have to worry about direction. Wait a second. I don't know anything about the distance that she's traveled yet. Looking at the problem, do you see how we have her traveling kind of at one speed for one time and another speed for another time? I think that's going to be important. Let's start labeling. We have a time here, delta t. Delta because time is passing. It's not like it's 0.5 on the clock. And we also have another delta t over here. Now those delta t's are different numbers, and she drives this one first and that one second. So I'm going to label this one delta t1, this one delta t2. Similarly, we've got a speed here. Well, I'm just more comfortable writing v average for speed. V average 1. It doesn't have a direction, does it? And we have a v average 2. And what's the variable that we're looking for? Pause for just a moment and label it. Don't cheat and just wait for me. Total distance. So let's use delta x. Total. Delta x total. Okay, here's a new statement, and I have to make this one up. Okay. Delta x total is going to be equal to delta x1 plus delta x2. And if you're with me, you probably realize how I'm going to find delta x1 and delta x2. It's going to be from this big physics equation. Time, velocity, and distance, time, velocity, and displacement, if it's required, are going to come together in this big physics idea. It's becoming very familiar by now. And I want to solve it for delta x, so delta x equals the product or the multiplication of velocity and time. Yeah, how fast you go and how long you do it. Delta x equals v average times delta t. And let's make this a little bit more useful, right? I don't have numbers for the total time or anything like that. I have numbers for the first part of her journey. So delta x1 equals v average 1 and delta t1. Okay, let's put these numbers in. Delta x1 equals 80.0 kilometers per hour times 0.500 hours. I hope you can see from here that this is an hours and a per hours. So hours on the top and hours on the bottom. Cancel out. I can see that our units are going to be good. Kilometers. Okay, 80.0 times 0.500. 3 significant digits times 3 significant digits. So that's going to be 40.0. What's our unit? Kilometers. Okay. At this point, I'll do the work for the second one and then add them together and write the answer down here while the video is paused. Okay, I calculated how far she went in the second bit. Her total distance is going to be the amount that she went in the first bit plus the second bit. And to be a little bit more clear here, maybe I'll write down here that this equals delta x total, because I'm now solving the whole problem. And that's going to equal 40.0 plus 60.0. Addition rules for significant figures, 1 decimal place and 1 decimal place. So my answer is going to be 100.0 kilometers. That's the rule. Nice friendly number. Okay, pause the video now if you need to review this. The next question. A ball initially at rest rolls down a hill and has an acceleration of 3.3 meters per second squared. If it accelerates for 7.5 seconds, how far will it move during this time? I've already labeled. Acceleration was named, time, distance, how far will it move? So that's what I need to know. And if you look at your equation sheet, you should find a pretty good fit. In order to have a good fit, though, you need to see that initially at rest is telling you that the initial velocity equals 0. So you have to make those words mean an equation or an initial condition. Look at your equation sheet now and pause the video until you find the big physics idea that has all these pieces and only one unknown. Don't cheat. Go ahead and look for the equation. This is the most important part. Okay, the equation you found on your library sheet is delta x equals initial velocity times time plus 1/2 acceleration times time squared. I do not write multiplication symbols between my variables, and delta x is just one thing. That is the change in time. So when I square it, it's a bit redundant to put parentheses around it. Okay, let's make a note here. We noticed that the initial velocity is 0. So this part is 0, and then anything times 0 is 0. This whole piece goes to 0. And that's how I usually write that a piece goes to 0. Delta x equals 1/2 a delta t squared. And this is the big idea that you need to start with. So this is required to be written down. Okay, now we can plug in some numbers. Delta x equals 1/2. Acceleration is 3.3 meters per second squared. Delta t is 7.5 seconds. I should stop myself and realize that I've already put a parentheses around this to help organize it. This is a habit of mine, because when I close that parentheses and remember the square, I see that I have every detail here. Here's the half. I got it. Here's the acceleration. I have every single detail of it. And here's the delta t, because I'm going to be squaring the number and squaring the unit. it's very easy to forget your squares as well. Okay, let's go through and calculate this. When I put this in my calculator, I'm going to look at it to make sure it's what it's supposed to be. Okay, 1/2 times 3.3 times 7.5 squared. Maybe a few notes. See how this is written a little bit strange. 1 divided by 2 times 3.3. Your calculator is going to treat that just like this is written. Nothing funny, like the 3.3 isn't down in the bottom. It handles these order of operations. We'll check that just for verification. Okay. It should be that. Let's check it in a different way. Let's see. 1/2 is the same as 0.5. 0.5 times 3.3. And 7.5 squared is the same as 7.5 times 7.5. I hope you agree this is a different way of writing the same thing. Good. Okay. I'll write this down and then round it. 92.8125 units. Seconds squared cancels with seconds squared. And that's good because my distance is in meters. And let's stop here and think about whether this answer makes sense. 92 meters is about the length of a football field. So a ball starts rolling, and after 7 seconds, could it possibly go a football field length? Wow, it's kind of a surprising thing. I guess it's going a lot faster than you could run. But it's a reasonable answer. So I'll go ahead and round it and box it. We had numbers being multiplied together. Something being squared is being multiplied after all, right? Just like I talked about here. So we're going to follow the multiplication rule. This half is exact. There's no significant digits in it at all, or infinite significant digits, if you will. So 2 times 2, our answer will have 2. Round it up. 93 meters. Okay. I almost literally asked, does anybody have any questions? A car moving due east increases its speed uniformly from 16 meters per second to 32 meters per second in 10 seconds. How far in meters did the car travel while accelerating? These notes here were made by a student that described this in class. But they're perfect labels. So we read, we try to imagine the situation, and then we label. Car accelerating from that fast to that fast. Initial velocity, final velocity, change in time, how far in meters. Okay, so that's going to be a delta x. Okay, take a second to look at your equation sheet and find something where you only have this as the unknown, and it only depends on this, this, and this. Don't cheat, look at your equation sheet. The equation goes like this. Your displacement is equal to the average of your initial and final velocities times how long it took. This is only true for uniform acceleration. This is only true for uniform acceleration. For this entire class, with the exceptions of like graphs and when we mention it, we're dealing with uniform acceleration, constant acceleration. Okay, so this is your good starting spot. Delta x equals 1/2 initial velocity plus final velocity times the time that passes. Okay, this could get a little bit tricky in your calculator. I know that a lot of students forget to put in parentheses, and if there's addition and multiplication, it can get a little bit messy. So I will do it step by step and then verify it. So 16 plus 32 is the first thing I'll do. Okay, 16 plus 32 is 48, isn't it? 48 meters per second. This is just as precise as these two were, right? I haven't rounded it. That would be a mistake. And now I'll plug them into my calculator, although I really don't need to. Let's see. Half of 48 is 24. 24 times 10 is 240. 240. Meters per second times seconds. Seconds on the top, seconds on the bottom. 240 meters is how far the car traveled. One final detail and one note is we have two significant digits times 3. So I could indicate this is the last significant digit, or I could convert it to scientific notation. 2.4, not 2.40, 2.4 for two significant digits times 10 to the 2 meters. 10 to the 2 from this reason. 1, 2. Let's also plug this in the calculator all at once, just so you can see how to do it. Okay, 1/2 times the sum of 16 plus 32 times 10. Excellent. Okay, thank you for going through this worksheet in detail, and hopefully you learned or reflected on some really important physics ideas.